Today we're going to look at 2.6, and in 2.6 we explore transformations. I have the parent function for y equals x squared here up on Desmos in red. And so we're going to look at what happens when we add and subtract and multiply other numbers throughout the parent function. The first one that we're going to look at is a vertical translation. And you can move your parent function up and down by adding or subtracting a value out on the outside. So now when I say outside, I mean it is in addition to whatever gives the function its name. So this is a squaring function. So x squared plus k out on the outside, the addition and subtraction happens after I say the square. Right now, when it's at 0, you can see that the blue and the red overlap. But as I make k a positive value, it's going to travel its way up the y-axis, and when it's negative, it's going to head down the y-axis. It is going to, that value of k is going to go the way that you think it would go. And so when you are looking to move functions, think about grabbing the y-intercept and dragging that up or down depending on the value of k. If it is inside of the function, like I see on the purple graph, then I'm going to say plus or minus before I say the square. So that's how I know that this piece, this h in here, is inside of the function. So if k makes it go up or down, h is going to make it go left and right, but maybe not the way that you would think. So as I make this a positive h, it's going to bring it over to the negative value. And when I make it a negative h, it's going to bring it over to the negative values, but notice on the inside this says negative. So if I change that to a positive, now when I make it positive, it goes left. And when I make it negative, it goes right. So on the inside, when you change your h value, it's actually going to go the opposite way that you would think that it would go. And those are going to be your horizontal translations. For stretches and shrinks, those can be a little touchy. Those can depend on the type of function that you're working with. Now, inside of the function, like you see here with the green, and the outside of the function, like you see here with the orange, they'll have similar effects, but one is going to have more of an impact than the other. Let's look at outside the function first. So a times x squared. So you're doing the multiplication by a after you say square it. So as a gets bigger and bigger, it squeezes this together into a shrink. And as it is in between 0 and 1, that's what's going to make it get wider. And then as it becomes negative, it's going to flip it upside down. The similar thing will happen when it's inside. But with your positives, it's going to happen much quicker. You can see there is when b is 2, where when a is 2, even though it's squeezing together, it's not happening as quickly. And that's because when I plug in a 2 for b, it is then going to get squared, and so that it actually looks like a 4. And then they're the same. A little bit different is what's going to happen with my negatives. So when I have it on the outside, and let's say I have a negative 2, you can see on this side, it never flips under. So at the negative 2, it's still heading up. That's because it's on the inside. And so the negative 2 gets squared And it stays now a positive 4. So that looks the same as what it did over here. And so when the absolute value of the coefficients of the x squared increase, that's going to squeeze them together. When they become negative, it's going to flip it upside down like a reflection. And when they're between 0 and 1, so that absolute value is smaller than 1 but bigger than 0, that's what's going to make it wider. Now, the shrinking and the stretching really depends on which way your function is facing. As x increases, does y increase? Or as x increases, does y decrease? And so we'll look at another example. Let's say that instead of talking about the squaring function, we're talking about the square root function. That looks like that. When I have inside of there a value, as that increases, you see it now how it's dragging it up. Now it dragged the other one up, but this up is certainly not a shrink, right? This is going to be a stretch, because this one, as my x's increase, my y's are my increase is heading out this way, so it's kind of facing to the right. Where with my x squared, he was facing up. So when it dragged the x squared up, it pulled it together, and so that it went up faster. Or squeeze, where this up actually makes it wider. And so the same thing will happen if I put it out on the outside, just much quicker. Well, before, when I put it on the inside, it was faster, and when it was on the outside, it was slower. That depends on the function. This outside actually keeps my c value being its whole full c value. Let's make it a 4. Where if it was on the inside, I'll have to use D since I've already used C, and I make it a 4. It actually winds up being like a 2, because this gets taken the square root of. So it's much more like that. And so when you multiply, it's basically going to be a stretch or a pull. Something's going to wind up going much faster or much slower. How much faster or how much slower? Or if it's actually higher or getting smushed down closer to the x-axis, depends on whether or not it is, it depends on the type of function that it is. Now we could put all of these concepts together into one big graph. So let's say that we wanted to talk about the x squared again, but now I'm going to have lots of stuff going on. And I'm going to leave my a out front here. Well, let's say I wanted to take my original x squared, and I want to move him so that my vertex is up here at, a 5, and maybe all the way over here at the 10. So if I want to bring this up 5, I would need to take that k value to a positive 5. And if I wanted to make that h over to the 10, I actually have to bring this out to the negative 10 to get it out to the other side. Now, what if I said this is too narrow? I need to widen this so that I can make it a little bit bigger. Maybe I need this purple piece to be closer to, say, 1510. So I would need to take my A and make it a little bit wider. Maybe I can get it close to being the 1510. Not quite. Oops. Maybe. Oh, there we go, 0.2. And so they can make it a little bit wider. If I wanted it to go faster and make this piece, these red one pull together, I would need to make it a higher absolute value. And if I wanted to flip it upside down, which you see a little bit more in practical applications, then my absolute value, my A value would have to be negative to flip him upside down. In WebAssign, you have the square root function that you'll have to move around here that looks like this. Well, almost the square root function. And I want to talk about if f is my blue function, f of x, what is f of x plus 2? Well, a plus 2 on the outside brings this up 2 units, and so it would be the second one. This plus 3 says take my blue over 3 units, but the opposite way that it looks. So 1, 2, 3 would put me at the 1. If I wanted to move to a positive 2, like I see right here, then I would have to put a negative 2 inside of the function. And so that would need to be number 3, which leaves me with number 4 for the f of x minus 4 to drag this down. What if I wanted to describe what is happening in these two? Well, you have a watch it here, so if you don't remember everything, you can pull that up. But you know that this plus 2 on the outside is going to move it up or down, and since it's positive, that's going to be 2 up. And so we're kind of done right there, right? Because there's only one that has 2 up. It's the inside that goes left or right, and it goes the opposite way. So if it says negative, it's actually going to make it positive. And so if it's positive, it's actually going to make it head over to the negative side. And so be over to the left 2, and then this is down 1. You can use Desmos to help you with this. You can pick your favorite f of x, any of those parent functions that you explored earlier on in the chapter, and just play with Desmos, desmos.com, and launch the calculator. And of course, you can also use the calculator that you have through the VTI or in person and graph some things that way too.